In this video, we are going to talk about singular value decomposition. This is the first of two overview slides, and this is the second. We're going to spend a few minutes, maybe up to 10 minutes, on the first two slides, these overview slides, before we go back and do each topic in more detail and with more examples. We start by getting inspiration from diagonalization of square matrices. So when we have a square matrix, we can write it as a product of three matrices, P, D, and P inverse. And we found that P would be equal to the matrix with the column vectors equal to the eigenvalues of A, and D is the diagonal matrix with the diagonal being the eigenvalues of matrix A. We'll discuss this in more detail later, but for now, I'm just going to say that then the problem with this, or not so much the problem, it was limited because it's limited to square matrices. So we can only diagonalize square matrices. We can only find eigenvectors, eigenvalues for square matrices. And so we want to do something for rectangular matrices that are m by n, not necessarily square. And that's what SVD comes in. It's for rectangular. So we're taking this matrix A and we want to factor it into a product of three matrices, and similar to this diagonalization, this matrix V is going to have the eigenvectors of a matrix A transpose A as columns. Why A transpose A? Well, first, we can't use the eigenvectors of A because it's not square. We can't compute them. But A transpose A is a square matrice, so we can compute eigenvectors. And then exactly why we chose A transpose A really depends on why we're decomposing this, what it is that we're trying to study, which we will get into on this next point here. And then second, this middle matrix, the sigma, we're going to take the eigenvalues of A transpose A and put them on the diagonal. The reason why we choose A transpose A is related to our next point, which is that eigenvalues measure the amount of stretch in an m by n matrix. And this we should know from the eigenvector-eigenvalue equation, because for an eigenvector x, ax equals lambda x. That is, the transformation of x is purely a stretching of the vector x, and how much it stretches is exactly lambda. If we wanted to study exactly what the norm of AX is or how it's lengthened, we take a unit vector, and then what we should be left with is lambda. That is, the norm of AX is equal to lambda x because it's an eigenvector. X is an eigenvector. And then we can factor out the constant lambda, and then x, again, we took the unit vector so that our final answer is lambda. And in this way, we see that the effect of A on x is the stretching by a factor of lambda, which means if lambda 1 is the eigenvalue with the greatest magnitude, so if you have a list of eigenvectors for A and lambda 1 is the one with the greatest magnitude, then its corresponding eigenunit vector is the direction in which the stretching effect of A is maximized. A couple of other notes: when we want to maximize the norm of AX, or the length of AX, because the norm has a square root, we can simplify our calculations by maximizing the norm of AX squared. And the norm here is just AX dot AX, converting it to a matrix transformation or vector transformation, that's AX transpose AX. And then to take the transpose of A and X, that's X transpose A transpose times AX, which means we have X transpose AX. So this is the matrix we're studying when we want to study how a matrix A stretches vectors, and in particular, what directions that A has the maximum effect on. Also, the max of X transpose AX, where magnitude of x equals 1 occurs at the greatest eigenvalue of A transpose A. We've already kind of mentioned that. And then that's why this matrix is central to the singular value decomposition. And also just note that A transpose A is symmetric. It's a square matrix, and we can take these eigenvectors, eigenvalues. And we're just about to go into this singular value decomposition, but let's talk about singular values, since that's where we get the name of. Just like this, the diagonal matrix in the middle gives us the name diagonalized squared matrices. Singular value, this matrix in the middle is a matrix of singular values. And singular value is a general term in mathematics, and it refers to non-negative real numbers arranged in decreasing order. In SVD, what we're talking about is the square roots of the eigenvalues of A transpose A are the singular values of matrix A. And just a warning, the singular values of A are not the eigenvalues. They're the eigenvalues of A transpose A. And let's see, what else? The singular values are the lengths of the vectors AV1, AV2, up to AVN, for this reason here, which is very similar to this reason. And then we have this last theorem, which we will directly use in our singular value decomposition. So suppose you're given an orthonormal basis of Rn consisting of eigenvectors of A transpose A. Remember, A transpose A is a square matrix, so it's n by n, so its eigenvectors will form a basis for Rn. And so if we have this basis from eigenvectors of A transpose A, this theorem says that if A has R non-zero singular values, then AV1, AV2 up to AVR is another orthogonal basis, and it's an orthogonal basis for the column space of A. So if we're given this one orthogonal basis of eigenvectors of A transpose A, we can come up with another second orthogonal basis for the column space of A. Now we can look at our singular value decomposition. So let A be an m by n matrix with rank R, so it doesn't need to be square. Then there exists an m by n matrix in the form shown below. So this is the same dimension as A, where D, the diagonal entries in D are the first R singular values of A. So the diagonal entries in this upper left-hand corner are the eigenvalues of A transpose A. Remember, they're not the eigenvalues of A, but the eigenvalues of A transpose A. And then we surround it by zeros until sigma becomes the same size as A. And then we have another matrix, orthogonal matrix U, and a third orthogonal matrix V, such that A is the product of the three matrices U, sigma, V transpose. Using our last theorem, which I have copied here for your reference, and also sort of the pattern from our diagonalization of matrix, we're going to take V as the matrix of the eigenvectors of A transpose A, and we're going to take sigma as the matrix with singular values of A on the diagonal, that is the eigenvalues of A transpose A on the diagonal, and then U is going to be the matrix constructed from AV1, AV2 up to AVR if there are R singular values. And again, this U matrix is this matrix here, which is the basis, the orthogonal basis for the column space of A. And what that gives us again is this decomposition that allows us to study the vectors, the directions where the matrix A has the most impact, the most stretching. And just a quick note, since U has matrices for every singular value, it may not actually cover Rm. So it might be the case that we have to augment U until it forms, or extend U until it forms an orthonormal basis for Rm. And our last example covers this case. So that's it for our overview. It's a little bit long since we actually have 2 slides in order to cover all our main points. But now we're ready to start our detailed look at singular value decomposition. And we will start by reviewing diagonalization of a square matrix. That is, when we factor A into the multiplication of 3 matrices, the first one being a matrix of eigenvectors, the second one a diagonal matrix with eigenvalues on the diagonal, and the third being our first matrix inverse. So looking at diagonalization, and if you need to review, it's in chapter 5.3, the video is called Diagonalization. We found if we want to put A into the form of P, D, P inverse, where D is a diagonal matrix, then D would be the diagonal entries will be the eigenvalues of our matrix A, and that the eigenvectors of matrix A become the columns of P. So for example, if A is a 2 by 2 matrix with column vectors -3, -2, 12, 7, we look at our eigenvalue eigenvector equation, which is A minus lambda I x equals 0. We find the determinant to give us the characteristic equation, and we find that our two eigenvalues are 1 and 3. To find the eigenvector associated with lambda equals 1, we put in 1 into our A minus lambda I, and we get the matrix -4, -2, 12, 0, and we're solving the homogeneous equation, so we have the 0, 0 here, and we find that our v1 vector is 3, 1. Similarly, for lambda 3, we find our v2 vector is 2, 1. So that means A equals P d P inverse, where P is equal to the eigenvectors 3, 1, 2, 1, and D is equal to the diagonal matrix with the eigenvalues on the diagonal 1, 0, 0, 3. So diagonalization was useful in many applications, but the limitation is we could only diagonalize and find eigenvectors as square matrices. So now we're going to consider a singular value decomposition for rectangular matrices, n by n matrix. And what we want is to be decomposed into the multiplication of three matrices: a matrix U, a matrix sigma, and a matrix V transpose. And similarly to our diagonalization, we're going to take V is going to be the matrix of eigenvectors, but the eigenvectors is not going to be of A because A is not square. We can't find the eigenvectors, but A transpose A is square. So we're going to take the eigenvectors of A transpose A. We're going to take sigma. On the diagonal, we're going to put the eigenvalues on A transpose A, and then we'll add zeros to sigma so that it's the same size as A. And then finally, we have this U matrix, which our last theorem gives us, but also I will derive later in this video how to find U. In our singular value decomposition, we take the eigenvectors and eigenvalues of A transpose A. So what is it that A transpose A allows us to study? That's answered by this next topic here, not by this next paragraph, by the next topic though, and that is that eigenvalues measure the amount of stretch of an n by n matrix. And we know that from our eigenvector eigenvalue equation. When we have an eigenvector x, then the transformation of A on that eigenvector is simply equal to a scalar multiple of x. So how much A stretches x is exactly the coefficient factor here, lambda. So if we want to study the stretch of AX, we take an eigenvector and we normalize it to unit length. And that way, when we take the norm of AX, that's simply equal to the norm of lambda x, because x is an eigenvector. And then we can factor out the constant lambda, and then we get, since this here, x, we normalized it, now this expression here is equal to the magnitude of lambda. So for vectors in the direction of this eigenvector, A will stretch it by an amount, lambda. So if A has a number of eigenvectors, if lambda 1 is the eigenvalue with the greatest magnitude, then its corresponding unit eigenvector, V1, is the direction in which the stretching effect of A is maximized. And so the idea is this description of lambda 1 and V1 here has an analog for rectangular m by n matrices that will lead to the singular value decomposition. We're going to continue with our analysis here so we can get to the A transpose A matrix. And just a quick note, to maximize the length of AX, which is equal to the square root of AX dot AX, we can maximize AX length squared. That's easier because it gets rid of the square roots. So this norm is defined as AX dot AX, translated into matrix multiplication. That's AX transpose times AX. Now the transpose of AX is equal to X transpose A transpose. And this step from here to here just comes from this property that if you have A, B transpose, that's equal to B transpose, A transpose. So here we have this, and then when we multiply this out, we get X transpose A X. So that means to maximize this A, the magnitude of AX, we want to maximize X transpose AX. To maximize X transpose AX, we're going to note that A transpose A is symmetric, and we use the definition of symmetry, so A is symmetric if A transpose equals A. So to prove A transpose A is symmetric, we're going to look at A transpose, which is equal to the second matrix transpose, A transpose, and the first matrix transpose. So it's A transpose transpose, but A transpose transpose is just equal to A. So that means A transpose is equal to A transpose A. And what does that give us? I can apply this theorem from 7.3, the chapter on constrained optimization. I did not cover this chapter, so I will look at this theorem now. Let A be a symmetric matrix and define M to be the max of X transpose AX. So in this case, our matrix A that we're looking at is A transpose A. Then M is the greatest eigenvalue of A, and the value of X transpose AX is M when X is a unit eigenvector of U1. So for our problem, that means the max of X transpose AX, where X is a unit vector, that occurs at the greatest eigenvalue of A transpose A. And I made that note right here, along with the last note that A transpose A is symmetric, it's a square matrix, and becomes central to singular value decomposition. Those were a lot of notes summarized here, and I have our first example. Given the matrix A, the linear transformation X to AX maps the unit sphere over here onto an ellipse. And it's actually not that important you know how to figure this out, but just know that it kind of maps from a circular shape to something that's stretched out on some axis. Find a unit vector x which the length of AX is maximized, and compute this maximum length where A is the 2 by 3 matrix with column vectors 4, 8, 11, 7, and 14, minus 2. So looking at my notes, the maximum of the length, AX is maximized, the length of AX is maximized at X transpose AX, and this is maximum. It occurs at the greatest eigenvalue, so I need to find of A transpose A. So I need to find the eigenvalues of A transpose A. So here I multiply A transpose times A. So I take the first row to make it a column 4, 11, 14. The second row becomes the column 8, 7, negative 2, multiplied by my 2 by 3, 4, 8, 11, 7, 14, negative 2. And I get this 3 by 3 matrix. And remember, whenever you multiply A transpose A, you're always going to get a square matrix. And it's a 3 by 3 with column vectors 80, 140, 100, 170, 140, 40, 140, 200. I have my A transpose A matrix here. I have my eigenvalue equation. Remember, I can do this now because we have a symmetric matrix. So I'm going to look at A minus lambda I. I'm going to find where the determinant is equal to 0 because that will tell me when my AX minus lambda IX equals 0 has a non-trivial solution. So I get my characteristic equation, and it was kind of ugly, but then I used Wolfram Alpha to simplify it for me. And to show you what Wolfram Alpha looks like, you go on the internet, look for wolframalpha.com. I selected algebra. I said I wanted to simplify an equation. I put in my characteristic equation, the unsimplified one. I used x instead of lambda because that's what it knows. And then I had this alternative form here, or this alternate form, which I used to solve for my eigenvalues. So using this, then my eigenvalues are lambda equals 0, lambda equals 360, and lambda equals 90. Because I am trying to maximize AX, I have this note here that AX is maximized when this is maximized, and X transpose AX is maximized at the greatest eigenvalue of A, so I only need to look at the eigenvalue of 360. So I plugged in 360 into my A minus lambda I matrix. So I still have the matrix A, but along the diagonal, I subtract 360. So 80 minus 360 gives me my minus 280. My 170 minus 360 gives me my minus 190, and my 200 minus 360 gives me my 160. And then I'm solving for the homogeneous equation. I row reduced using Wolfram alpha again, looking under linear algebra reduced matrix. Then I get that my eigenvector v1 is equal to 1, 2, 2. So I normalized by, what would this be? 1 squared plus 2 squared plus 2 squared, that would give me 9. Square rooted is 1/3. And I'm just going to copy this answer over here so I can erase this other stuff and free up some space. So again, this tells me the magnitude of my greatest stretching, and this tells me the direction. So if I want to know the actual AX, the magnitude of AX, I need to put in my A and my vector V or X, 1/3, 2/3, 2/3, and I get 18, 6. And that's actually, if you have this sphere to ellipse, that's along this major axis, which is what you would expect, because, right, that's where the maximum stretching of the spherical thing is. So for X being normalized, the maximum of AX is equal to AV1, where V1 is an eigenvector, which is equal to lambda V1, which is equal to, this is a lambda, it's a scalar. We can pull out the scalar, so this should just be the absolute value times our vector. And if V1 is normalized, that's simply equal to our lambda, magnitude of lambda, and magnitude of lambda is the square root of 360, our lambda, which is equal to 6 square root of 10. So singular values is where singular value decomposition gets its name. And singular values is a general mathematical concept, and singular values refer to non-negative real numbers arranged in decreasing order. But again, the name of singular value decomposition comes from singular values because this middle matrix here, this sigma, is composed of singular values. In the same way, when we do diagonalization, it's the middle matrix that's diagonal. But anyway, to define a singular value, the square roots of the eigenvalues of A transpose A are called the singular values of A. So be careful, because the singular values of A are not the eigenvalues of A. The singular values are the eigenvalues of A transpose A. And another fact, the singular values are the lengths of the vectors AV1, AV2 up to AVN for this reason here outlined, which is very similar to the reasoning here we had an eigenvalues measuring the amount of stretch of a matrix. So coming back to our last example where we had this matrix A, which was the 2 by 3 with column vectors 4, 8, 11, 7, 14, negative 2, and it kind of stretched this sphere into this ellipse. And we said that the maximum eigenvalue was 360, but the other eigenvalues were 0 and 90. That means sigma 1 is square root of 360, sigma 2 is square root of 90, and sigma 3 equals 0. And these are the three singular values of A, the max of which is square root of 360. Technically, we need to show that these square roots of eigenvalues are non-negative in order to call them singular values. And so here's the proof. I don't really want to go over it except to say that I showed that the lambda is equal to some quantity squared. And since it's a quantity squared, it must be positive. So now that we know what the singular values are, we're getting really close to singular value decomposition. But first we have to introduce this theorem, which we're going to use in singular value decomposition. So suppose V1, V2 up to Vn is an orthonormal basis for Rn, consisting of the eigenvectors of A transpose A, again, this matrix here that we saw up here, arranged so that the corresponding eigenvalues of A transpose A are arranged in decreasing order. So suppose A has R non-zero singular values, then A times V1, A times V2, A times Vn, that's our A times our eigenvector, is an orthogonal basis for the column space of A, and the rank is equal to R. I cleared out some stuff. I'm going to show you an outline of the proof, but just because to save time on my video, I'm going to skip this proof, but it is kind of important you know what it says. So it says we're given an orthonormal basis of Rn consisting of eigenvectors of A transpose A. Remember, A transpose A is a square matrix and it's n by n. So its eigenvectors, if you remember our chapter about eigenvectors, its eigenvectors will form an orthonormal basis of Rn. So this is given to us. And they're arranged however they're arranged. Now, suppose A has R non-zero singular values. Remember, the singular values of A are the eigenvalues of A transpose A. Then we're given this next set of vectors. That's AV1, AV2 up to AVR. So A times the eigenvectors up to R, because we have R singular values. Now this set is going to be an orthogonal basis for the column space of A. As I had mentioned, I have outlined the proof for you here. First, I show that this set is linearly independent. Then I show that they span the column space of A, and therefore the set is a basis for column space of A. And last, to show it's an orthogonal basis, I showed that the vectors are orthogonal to each other. And so this is the outline of the proof. Again, I didn't really want to spend time on it, but it's here for you. But do take a look at this theorem because we will be using it. And now we've covered the first page of our overview, and we are ready for the second page, which gets to the singular value decomposition. Fortunately, all the other stuff has worked up to this, so this part should go maybe a little bit faster. But the idea is we have A, it's a rectangular matrix, M by N. So there exists an M by N matrix in the form showed below. That's our sigma, for which the diagonal entries in D are the first R singular values of A. So now we know what the singular values of A. Those are the square root of the eigenvalues of A transpose A. And then there exists an M by N orthogonal matrix U and an N by N orthogonal matrix V, such that A equals U sigma V transpose. And what we're going to see is these are sort of the instructions on how we're going to construct V, sigma, and U. But I want to sort of derive that just so you get a feel for why this is true. So this is my proof, not so much a proof as a derivation, but same thing. And as I said, I mentioned, we're going to use this theorem here where we start with an orthonormal basis consisting of eigenvectors of A transpose A, and then we're going to get this second set where if A has R non-zero singular values, we multiply the corresponding eigenvectors times A, and this is going to give us a second set. And no surprise, our two sets of vectors here, they become the column vectors of U and V. And we've chosen to look at A transpose A because we want to study which directions the matrix A has the most impact as it stretches out a vector space. So we're going to let V consist of the eigenvectors of A transpose A. So let V, V1, V2 up to Vn be the orthonormal basis of Vn consisting of the eigenvectors of A transpose A arranged such that corresponding eigenvalues of A transpose A are arranged in decreasing order. And then along with the information about the eigenvectors of A transpose A, we're going to make D the matrix of the eigenvalues of A transpose A. That is, D is the diagonal matrix with our singular values on the diagonal. So it looks like here is our diagonal matrix of singular values, and then we add zeros to make sigma the same size as A. And now because our singular values are arranged in decreasing order and our matrix V, the vectors are arranged according to the sigma, these two vectors kind of match up to give us a nice picture of what's going on with A transpose A. So now comes the hard part. We can do anything, try out a V and a D, but now you need to construct U so that A is equal to U sigma V transpose, right? This part is where we actually have to make things work. So to construct U, we're going to consider U times sigma. So if we make U times sigma equals to AV, then U sigma V transpose, that's how we want to decompose A, is going to equal to, if U sigma equals AV, it's going to equal to AV V transpose, and then these two together make I, and that equals to A. So our big strategy is to choose our U so that U sigma is equal to AV. So let's look at U sigma. U sigma, we have our U is a matrix. It has column vectors U1, U2 up to UM. And then our sigma, again, it has these R singular values and then zeros everywhere else. And then we add zeros to make it the same size as A, M by N. But this diagonal matrix with all the zeros, when you multiply our U matrix times this diagonal matrix, you're going to get sigma 1 U1 times the first column vector. Sigma 2, this is going to be our first vector in column vector of U sigma. Our second column vector of U sigma is going to be sigma 2 U2, and then our rth column vector is sigma R UR, and then zeros padding along. So if we want this here, this U sigma to equal to AV, it better look like AV1, AV2 up to AVR 0, 0. So what we have is, kind of equating column vector by column vector, I guess. Sigma of IUI is equal to AVI, which means that our U sub I is equal to 1 over sigma I times AVI. So this is our formula for each column of U, and this is what is going to make this decomposition work. The one warning I have is sometimes you won't have enough eigenvectors for U. Once you, well, one, you have to normalize, which we do with this here. But if we don't have enough eigenvectors to form a basis for Rm, we're going to have to extend that basis, and it needs to be orthonormal. And I have an example on how to do this. And then last note, by construction, U and V are orthogonal matrices, and AV is equal to AV1, AV2, up to AVR, and that's equal to sigma over U1, sigma U2, sigma UR up to, and then zeros. And I'm having trouble talking because I've been at this for hours looking at this chapter. For an example of the singular value decomposition, I'm going to use the previous example where A is the 2 by 3 matrix with column vectors 4, 8, 11, 7, 14, minus 2, and it takes this sphere and flattens it into and stretches it into an ellipse. We had our first eigenvalue-eigenvector pair. The eigenvalue was 360. The eigenvector was 1/3, 2/3, 2/3. Our second eigenvalue was 90, so I'm going to plug in my 90 into my A transpose A minus lambda I. So I have A transpose A gave me this matrix, the 3 by 3 with column vectors 80, 100, 40, 100, 170, 140, 40, 140, 200. So my A transpose A minus lambda I, kind of putting it into my eigenvector-eigenvalue equation, I have 80 minus lambda, my 170 minus lambda, and 200 minus lambda on the diagonals. The rest is the same. I'm going to plug in lambda 2 equals 90. So here I'm going to get on the diagonal 80 minus 90 is minus 10. Over here on the diagonal 170 minus 90 is 80. And on the diagonal 200 minus 90 is 110. The rest of the numbers are the same. I was going to do the row operations, but I got lazy and I plugged it into Wolfram Alpha. It's equivalent to this 3 by 4 matrix with column vectors 1, 0, 0, 0, 1, 0, 1, 1/2, 0, 0, 0, 0, which told me that x3 was free, x2 is equal to 1 minus 1/2 x3, and x1 is equal to minus x3. I chose x3 to be equal to 2 to get rid of this fraction, and I get v3 is equal to minus 2, minus 1, 1. But to normalize, I need to divide by 2 squared plus 1 squared plus 2 squared is 4 plus 1 is 9, square rooted is 1/3. So I have minus 2/3, minus 1/3, and 2/3. That's my second eigenvector. And then for the eigenvalue equals 0, I just get my matrix A, augment it because I'm solving the homogeneous equation, I see that x3 is free, x1 is equal to 2x3, x2 is equal to minus 2x3, so I get the vector 2 minus 2, 1, normalized as 2/3 minus 2/3 and 1/3. So here's my third eigenvalue eigenvector pair. And again, these are eigenvectors and eigenvalues of A transpose A. You know, A won't work because it's not a square matrix. I have my three eigenvectors here, and as I said, the V matrix, you know, just taking a kind of some inspiration from diagonalization, I'm going to have my V matrix now based on my eigenvectors. So my first eigenvector V1 is 1/3, 2/3, 2/3. My second eigenvector V2 is minus 2/3, minus 1/3, 2/3. And my third eigenvector V3 is 2/3, minus 2/3, 1/3. My D, my diagonal, I'm going to put my eigenvalues on the diagonal. That's square root of 360 and square root of 90. I'm sorry, these are not the eigenvalues. These are the singular values, which are the, where it is, I don't have my definition. It's the square root of the eigenvalues. So now my sigma, though, it needs to be the same size as A, which is 2 rows, 3 columns. So I need to add another column of zeros. I want this again to be the same size as A. So I have my V, I have my sigma, and now I need my U. And remember, U is designed so that U times sigma is equal to AV, so that when I multiply U sigma, when I multiply that, and that's equal to AV, my V and V transpose can become the identity, and then I'm left with A. But anyway, that's how we derive the formula for U, but it's 1 over sigma AV1. So I have 1 over sigma 1, my A, and my first eigenvector. So I did my 1 over sigma, I did my matrix multiplication, and I get this 18/6. And then my sigma 1 is the square root of 360, which is 6 square root of 10. So my U1 is 3 square root of 10, and then 1 over square root of 10. U2 is 1 over sigma 2, AV2. So I have 1 over sigma 2. I have my A and my second eigenvector. So I have my sigma time, or 1 over sigma, which is square root of 90, which is 3 square root of 10, times this calculation becomes 3 negative 9. So I have 1 square root of 10 and minus 3 square root of 10. So that means my A is equal to U. So I have my U1 here, 3 over square root of 10, 1 over square root of 10. My U2 over here, 1 over square root of 10 minus 3 over square root of 10. My sigma, which is 6 over square root of 10, is 0. And then 0, 3 over square root of 10, 0, 0. And then my V transpose, be careful, this is V transpose, not V. So the first V1 is my first row, 1/3, 2/3, 2/3. The second V2 is my second row, minus 2/3, 1/3. Oh, that's minus 1/3, 2/3. And my last V3 is my third row, 2/3 minus 2/3, 1/3. I moved up my A times U sigma V transpose. And remember, the thing about the U sigma, I wanted that to equal to AV. So when I multiplied U sigma times V transpose, my U sigma would be equal to AV. And then when I multiplied by V transpose, these two become the identity matrix, and I get back A, which is exactly what I wanted, right? I want A to be U sigma V transpose. So I just multiplied U times sigma as a double check. So this is my U matrix, this is my sigma matrix, and I actually get A times V, which is really nice because, you know, I multiplied A times V just to kind of double check. And I can also multiply U sigma and then V transpose. That's actually really what I should be doing. And I see that I get back A, so I have the correct answer. Ugly arithmetic, except I guess you and I are capable of it, so here it is. To put this singular value decomposition in perspective of our bigger problem, so here was our original problem. We had this matrix A that transformed this unit sphere into a flattened ellipse, and our original problem was, this is before we talked about SVD, find a unit vector x at which the length of ax is maximized and compute its maximum length. So we were looking for three things. One, we wanted a unit vector x. Two, the maximized ax. And three, its maximum length, although really these two questions are the same thing. But anyway, we used A transform A because that is the matrix that talks about maximizing the lengthening of A, or the lengthening effect of A. And we found the eigenvalue 360 and its corresponding eigenvector. And then we could plug in our A times the eigenvector we found, and we would find AX. So we had found our unit vector, that's our eigenvector here, and we found what the maximum length would be. That would be the square root of our eigenvalue. Also, you could do this by plugging in AX, and then you find 18. If you look at the length of 18, it's 360. So let's compare this to the singular value decomposition. The singular value decomposition takes A and it gives us three matrices, this U, the sigma, and actually I'm really more interested in this one here, which is V, not so much V transform, even though V transform is the one we use in the SVD. So we have these three matrices, and these three matrices answer exactly these three questions, right? The vector, which length is maximized, that's given to us by V. It's this first vector. Which direction has the second most impact? Is A lengthen second most? That's the second vector. And then which direction does A have the third most impact? That's the third vector. How much of an impact does it have? Well, that's measured by the eigenvalues. That tells us how much the lengthening impact it has. So that question is answered here by sigma. And then last, this matrix here, we're looking at AX. If you look at what U is, it's the normalized version of AX. So when you multiply U times sigma to like kind of unnormalize it, then you get this answer AX here, which is this point over here. So, for this problem, it wasn't a big deal to go through this analysis, mainly because the matrix that A transpose A is this, 3 by 3 matrix. But what if you had 100 variables? Or what if these numbers were really ugly or really big, just something that was unwieldy? Then what you would do is you'd plug in your matrix into a singular value decomposition package. They have one in MATLAB, and you'd get these three matrices. And from your three matrices, you can answer all of these questions. And again, about multiple vectors, how much does the transformation actually lengthen in this direction? You come over here and you find, well, this isn't a good one. This one here, you come over here and you find the eigenvalue. So that is what the singular value decomposition is useful for. This is an example where we're going to have to extend our U to form an orthonormal basis. So the example is to construct a singular value decomposition of A, where A is the 3 by 2 with column vectors 1, negative 2, 2, negative 1, 2, negative 2. So much calculation. So we construct V by using the eigenvector eigenvalues of A transpose A. So here I have multiplied A transpose times A. So A transpose takes the first column and makes it the row 1, negative 2, 2, takes the second column and makes it the row negative 1, 2, negative 2. And then A is the 3 by 2 with column vectors 1, negative 2, 2, negative 1, 2, negative 2. When you multiply, again, you always get a square matrix when you multiply A transpose A, and it's the 2 by 2 with column vectors 9, negative 9, negative 9, 9. At least this is kind of be easy to row reduce. At least that's what I think anyway. So looking at the eigenvector eigenvalue equation, and I put in the standard eigenvector eigenvalue equation, but understand that this A stands for the matrix here, this matrix, which is A transpose A. So anyway, so I took my A minus lambda I. So here I'm going to subtract lambda on the diagonals. I get my characteristic equation, which gives me that lambda 1 is equal to 18 and lambda 2 is equal to 0. So this is the problem here, the problem child. Anyway, lambda equals 18, so I put that into A minus lambda I. So when it's equal to 18, on the diagonal, I have 9 minus 18. That gives me minus 9. this 9 here minus 18 gives me another minus 9. And these other non-diagonal entries stay -9. And then I have 0, 0. Oh, this is easy to row reduce. I get x2 free, and x1 is equal to negative x2. So my first eigenvector associated with lambda equals 18 is 1, negative 1, which I normalize. So I have 1 over square root of 2 and minus 1 over square root of 2. I went ahead and did lambda equals 0, even though it's a problem child. So here's my a minus lambda I, but of course lambda is just 0. So I get back my matrix A transpose A with the 0. It row reduces to the 2 by 3, 1, 0, negative 1, 0, 0, 0. So that means x2 is free and x1 is equal to x2. So v2 is equal to 1, 1. I normalize and I get 1 over square root of 2, 1 over square root of 2. So far my v, oh, I guess I had to do this. My v is equal to my matrix of eigenvectors, which is 1 square root of 2 minus 1 square root of 2, and then 1 square root of 2, 1 square root of 2. So this is my matrix V. And remember, these eigenvectors are in order of size of eigenvalues. So I calculate the highest eigenvalue eigenvector first, and I make it my first column vector of V. Now I took this V here and I copied it up here with my lambda 1 and my lambda 2 just for future reference so that I can clear some other stuff out. So now I can construct sigma, and sigma has my singular values on the diagonal. Singular values, remember, they have to be greater than or equal to 0. So lambda 2 doesn't count. The 0 here doesn't count. I only have one singular value, which is square root of 18, or 3 square root of 2. So my sigma needs to be the same size of A. So I have my 3 square root of 2 in this upper left-hand corner, and the rest of the entries are 0. And now I have my sigma and I have my V, so all I have left is my U. Of course, as I had mentioned before, this is the U where we need to extend the bases. But let's get a start. So U1 is equal to AV1 over sigma 1. So I have my AV1, I have my matrix A, which is the 3 by 2 with column vectors 1, negative 2, 2, negative 1, 2, negative 2, times V1. My V1, I'm just going to pick it off of my V matrix, is 1 over square root of 2 minus 1 over square root of 2, and that gives me the vector 2 over square root of 2 minus 4 over square root of 2 and 4 over square root of 2. So U1 is equal to our sigma 1. That's the square root of our first eigenvalue, which is 1 over 3 square root of 2. So U1 is equal to our sigma 1 dividing our V1. So U1 is equal to 1/3 minus 2/3 and 2/3. So far so good. Now sigma 2, I tried to do the same thing for sigma 2, but I got 0. And I guess that was to be expected since the eigenvalue was 0, meaning, A times the eigenvector would give me 0. So I only have one basis vector, but remember U needs to be, where is it? It tells me in my theorem, n by n. So it needs to be, n in this case is, A transform A. Oh, it needs to be 3. It needs to be a basis for R3. I'm sorry I don't have A transpose A, but it's a 3 by 3. So I need to extend U to be an orthonormal basis for R3. And the way I'm going to do that is say, well, if I have a U2, when I dot it with my existing U1 over here, my 1/3 minus 2/3, 2/3, I should get 0. So I'm going to dot U2, another basis vector, with U1. So here I have the coordinates for my vector U2. My coordinates are U1, U2, U3. They don't have a little arrow on top because these are coordinates, not vectors. So this is the coordinates for my vector U2, and I dot it with my vector U1, which is 1/3 minus 2/3, 2/3. And I get the equation 1/3 U1 minus 2/3 U2 plus 2/3 U3 equals 0, and it equals 0 because I want them to be orthonormal. I want them to be orthogonal. And that's going to imply that u2 and u3 are free, and u1 is equal to 2u2 minus 2u3. Just solving, oh, I should say that it's equal to 0, sorry. Let me correct that. Equals to 0 because I want them to be orthogonal, and that implies that u1 is equal to 2u2 minus 2u3. So the basis for that, u2, the u2 vector, is equal to 2, 1, 0 times this coordinate u2 plus minus 2, 0, 1 times the coordinate u3. In other words, these are my two now bases, and both of these are orthogonal to u3 by design. To u1 over here by design, but we don't know if they're orthogonal to each other. So we need to use Graham-Schmidt. So I shrink things down because I'm running out of space. So I have my three vectors. Here, u1, 1/3 minus 2/3, 2/3. My second vector, u2, 2, 1, 0. And my third vector, negative 2, 0, 1. And the thing is, the last two vectors, this u2 and u3, by design, right, how we calculated them, they are orthogonal to my 1/3 minus 2/3, 2/3, my u1. However, these two, while they are a bases, they're a bases for vectors that look like the first coordinate is equal to 2 times the second coordinate minus 2 times the third coordinate. They're bases for this space here. There's nothing in here that says they are orthogonal. They're bases, they're linearly independent, they span a space, blah, blah, blah. But we don't know if they're orthogonal. So we need to apply Graham-Schmidt to these two vectors. And again, we don't need to do this first vector, u1, because by design they're orthogonal to u1. Here I have the formula for Graham-Schmidt. So we're given a basis x1, x2, xp. So our first orthogonal basis vector we'll just take that equal to x1. Our second orthogonal vector is our second basis vector minus the orthogonal projection of x2 onto v1. That's x2 dot v1 over v1 dot v1 times v1. So x1 now is equal to 2, 1, 0. My x2 is negative 2, 0, 1. My v1 then is just equal to x1, which is 2, 1, 0. My v2 is equal to my x2, which is negative 2, 0, 1, minus x2 dot v1, which is minus 2, 0, 1 dot 2, 1, 0, over v1 dot v1, which is 2, 1, 0 dot 2, 1, 0, times v1, which is 2, 1, 0. So that's minus 2, 0, 1, plus, because of this negative, 4/5, 2, 1, 0, which is equal to negative 2/5, 4/5, 1. Now we need to normalize v1 and v2. So v1 normalized is 2 over square root of 5, 1 over square root of 5, 0. v2 normalized is minus 2 over square root of 45, 4 over square root of 45, and 5 over square root of 45. Okay, I just moved these vectors over here as u2 and u3 because now this is my u1. Just going to circle it because we're really close now being able to make our u, our matrix U. So now I have my A equals U sigma V transpose, where U are these vectors here. My first column vector is 1/3 minus 2/3, 2/3. My second column vector is 2 square root of 5, 1 square root of 5, 0. And my last column vector is negative 2 over square root of 45, 4 over square root of 45, and 5 over square root of 45. My sigma I had gotten over here. It's the 3 by 2 with column vectors 3 square root of 2, 0, 0, and 0, 0, 0. And then by V transpose, make sure you do V transpose, not V. So V1 transpose is 1 minus square root of 2. So I'm just reading the rows now because I take my first column vector and make it into a row. My second column vector becomes my second row. 1 over square root of 2, 1 over square root of 2. And if you multiply this out, this should come out to be equal to A. But I'm done now because I'm kind of very tired. So this is where, well, actually I'll do a quick review over what we've covered and then I will finish. To review what we have done in this video, we talked about singular value decomposition, and we started with review of diagonalization of a square matrix, where we make A into a product of three matrices, one a matrix of eigenvectors of A, the second a diagonal matrix with the eigenvalues of A on the diagonal, and then the third matrix P inverse. And one thing about this diagonalization is we could only diagonalize and find eigenvectors of square matrices. So now we're going to do a decomposition of the matrix A, but we're going to consider rectangular m by n matrices, and we're going to decompose A into a product of three matrices again. And in this case, our matrix V is going to be the eigenvectors of A transpose A, and our matrix sigma is a diagonal matrix with the eigenvalues of A transpose A on the diagonal. And then, what matrix again were we going to use the eigenvalues and eigenvectors are? We used A transpose A, and that is an important matrix when we talk about how eigenvalues measure the amount of stretch in an m by n matrix. See how I transitioned there? It wasn't that great. But anyway, the idea is we know eigenvalues measure the amount of stretch because of the eigenvector-eigenvalue equation. When we have an eigenvector, then ax equals lambda x. So in other words, the transformation of A on x simply stretches x by a factor of lambda. So the eigenvalue lambda measures the amount of stretch. And then we can study the magnitude of ax. Usually we study the norm of ax squared, which gives us, through this calculation here, x transpose ax. And we also have the note that the max of x transpose A transpose x occurs at the greatest eigenvalue of A transpose A. And because our matrix V is dependent on the eigenvectors of A transpose A, as well as sigma on the eigenvalues of A transpose A, and U is based on A transpose A as well, this decomposition gives us information about how A stretches and affects different eigenvectors. Before we introduced the singular value decomposition, in other words, how we find U, sigma, and V transpose, which equals A when we multiply them together, we looked at singular values of an m by n matrix. And first, I'm going to tell you that the singular values, that's a term in mathematics, and it refers to non-negative real numbers arranged in decreasing order. So that does not include zero, does not include negative numbers. So when you're looking for eigenvalues, if you have negative or zero, they don't count as a singular value. And the singular value, those are the square roots of the eigenvalues of A transpose A. They're called singular values, and they're denoted with the sigmas. And the singular values are lengths of the vectors AB1, AB2, ABN for this reason here. And we used this theorem here directly when we did our singular value decomposition. It says, suppose we're given V1, V2, Vn, and it's an orthonormal basis of Rn consisting of eigenvectors of A transpose A. Remember, A transpose A is square, it's n by n, so its eigenvectors of a square matrix form an orthonormal basis for the space that they cover. And in this case, since it's n by n, it's for Rn. So we're given this orthonormal basis consisting of eigenvectors of A transpose A. And then we arrange those vectors according to their eigenvalues. And then suppose A has R non-zero singular values, right? The singular values have to be non-zero. Then AV1, AV2 up to AVR, the R singular values, is also an orthogonal basis. And it's an orthogonal basis for the column space of A. So this theorem, we're given an orthogonal basis, and it gives us a second orthogonal basis. And these are the two bases we're going to use over here in our singular value decomposition. For our singular value decomposition, we're going to take A and make it a product of three matrices. And when we take A, what we want to study is how A stretches different directional eigenvectors, and for that reason, we're going to study A transpose A. So V is going to be the matrix of eigenvectors of A transpose A, arranged so that the corresponding eigenvalues of A transpose A are arranged in decreasing order. Since it's a set of eigenvectors, it's a basis. Then our sigma is going to be the singular values of A. That is, it's going to be the eigenvalues of A transpose A on the diagonal, and then we add zeros to sigma until it's the same size as A. So notice how sigma and V go together, because the first eigenvalue on the diagonal of sigma goes with the first eigenvector of V. Then last, U is the matrix composed or constructed from AV1, AV2 up to AVR if there are singular values. And it's an orthogonal basis for the column space of A, and it's normalized. And then sometimes, as we saw in the last example, we might need to extend U, so from R vectors into M vectors, so that it becomes an orthonormal basis for Rm. I am planning to do one more video that has some examples of applications of singular value decomposition, a much shorter video than this one, but that concludes this video. Thank you for watching.